Other students? So can someone give me a suggestion? What method should I use for part A to factor this? Greatest common factor. And what is the greatest common factor? 5 and x, right? So when you write a greatest common factor, you're going to pull out 5x from each of those two terms. So if you divide them by 5x, what would you have left? Does everyone have this page? It's 15b. I should have given it to you today with that new agenda. Yes, you all have it. All right, so what do I have left? If I divide these by 5x and by 5x, I would have x left minus 2. On this, okay. B, what strategy should I use on B? So this was greatest common factor. You got 3 strategies to pick from left. There's 2 terms, and there's no greatest common factor. So what is it probably going to be? Difference of squares, right? 4x squared is a perfect square, 9 is a perfect square. You take the square root of each of them. So 2x3, 2x3, and just one gets a plus, one gets a minus. Like this should be screaming at you difference of squares. Because 2x times 2x is 4x squared, outer plus inner adds up to 0, and 3 times negative 3 is negative 9. All right, I got 2 left. What are my other 2 strategies? This is the diamond. I need the factors of 30 that add up to 13. So what are my factors? 3 times 10, right? And then once you've got these, those are the factors inside your parentheses. So x plus 3 times x plus 10. These are very different factoring strategies. That's the order I always go through in my head, though. Is there a greatest common factor? Is it difference of squares? Can I use the diamond? Okay, if all else fails, I'm going to have to do the box, right? Because it's 3x squared right here. So to do the box, you're going to set up 3x squared up here, 5 down in the bottom, and we're going to have to strategically split up that 8x. The way you split it up is you're to do the diamond, but you're going to do 3 times 5 is 15, and the sum has to be 8. So it has to be 5 and 3. So those are not just inside the parentheses like over here. Those are inside these other 2 boxes, 5x and 3x. So now I'm ready to do the outside of my box to get my factors. So one of these needs to be a 3x. So I'm going to put the 3x up here so that I can get this 3x by multiplying by 1. So 3x times 1 is 3x. 3x times x up here will give me 3x squared. And then this must be a 5, right? X times 5 and 1 times 5. So your final answer is 3x plus 5 and x plus 1. So I just did those 4 examples with you. There basically is one of each example down below in number 2. So figure out which one is which, and then you have to solve it. So if you have to solve it, like for example in C, the answers would have been -3 and -10, right? The x-intercepts. So I'm going to just give you a few minutes to try example 2 on your own, the same way we just did example part A, or 1. Gotten to the end? All right, so this first one was a trinomial. It doesn't have a greatest common factor, so you're going to go in to do the diamond. So you're looking for the factors of -40 that add up to -3. So -8, +5. So x minus 8, x plus 5 are your factors. So what are my x-intercepts? So because this says equals 0, I need to actually find my x-intercepts. So what will make that 0 for x and what will make that 0? Well, it's actually going to be +8 and -5. So your x-intercepts are actually going to be opposite of what your factors are, because doesn't 8 minus 8 make that 0? And -5 plus 5 makes that 0. So those would be the x-intercepts on the graph. These are the factors that we're going to need for solving some rational function stuff later. I think most of you figured out B was difference of squares. X plus 12, x minus 12. So your two x-intercepts would be -12 and +12, right? Or plus or minus 12. Those are your two x-intercepts. All right, and then I think most of you figured out that C was the greatest common factor problem. So I'm going to pull out a 6x, and I'd have x minus 2 left. So then x has to be 0 here, and x has to be +2 there. 0 and +2 are my x-intercepts. So make sure you go all the way if it's set equal to 0 and it tells you to solve it. Up here, we stopped at the factoring step because it just said factor. So I think most of you at least now can do 2 out of the 4 methods pretty well. Some of you 3 out of the 4. And the box method one, yep, that one's just a little bit harder. So like there would only be maybe one of those questions on the test, or, you know, it'd be in a multiple of, you know, a few of these. So I know the box method is the hardest. I won't focus on it, but it'd be nice if you could factor bigger polynomials like this. So 5x squared minus 8 goes in the box. And if you're setting up the diamond, the -40, because it's 5 times -8 is -40, -18 is the sum. So I think some people, this is a harder one, but it would be -20 times +2 is -40 and adds up to -18. -20x and 2x go in your box. So if you didn't get a chance to get that far, why don't you see if you can do the last step of the box yourself? I'll just give you like 10 seconds or so. So you know that 5 is prime, so it either has to be 5x times x or 5x times x. You want to put the 5x wherever it's going to be across from the 20, because 5x can multiply by something to get you that -20. So -4, right? 5x times -4 is -20x. X times 2 is 2x, and that does multiply to get you -8. So your factors are x minus 4 and 5x plus 2. And your final answer is x would be +4 or -2/5. Because this 5x plus 2, I did it in my head, but if you actually set 5x plus 2 equal to 0, you'd have to subtract 2 to the other side, and then you'd have to divide both sides by 5. So that's where the -2/5 comes from as an x-intercept. Don't just look at this term and say the answer is -2, because it's -2/5. So factoring, if you still need more help on factoring, then we need to focus on that kind of these next couple days. So number 3 is kind of a different type of question, but I felt like we could use a little bit more practice on it. So this is giving you a function. What's the rate of change between day 1 and day 5? What's the instantaneous rate of change at 2 days? On what day is the instantaneous rate of change the highest, and what's the maximum population of flies? So your first step is going to be to put this into a graphing calculator. So you're going to go to your y equals menu and clear out whatever's in there, and make sure that the plots are not on. See how mine, none of them are highlighted? If you have a highlighted plot, you need to arrow up and hit enter. See how that's highlighted now? Arrow up, hit enter, arrow down. You don't want them highlighted. That's for scatter plot graphs. So I'm going to enter in 230 divided by parentheses, 1 plus 56.5. E is a constant that you might not have seen before. We're going to look at it this year in exponential functions. It is located over the division symbol. So if you hit second division symbol, there's the E. And then to raise it to a power, you're going to use this upside down V shape. That's the exponent key. See how that gets me in the exponent? Negative 0.37x. I'm using x as my variable. They use t in their function for time, but I'm just going to use x as my variable. Can people type that in okay? That one's just kind of a tricky notation. You got to find the e. You got to raise it to the negative 0.37x power. And then we're going to go look at our table of values. Did anyone have trouble entering that in? So if I go to second table setup, we should start at hour 0 and count by an hour at a time. So go to second table setup, it's above the word window. Start at 0, count by 1, and then go to second table. So the initial population of flies was 4, and then here's the population growing a little bit more each day. And if you scroll down, eventually it'll plateau out. I don't know what it plateaus at. Still going up a little bit. Looks like around 2:30 maybe is where it's going to plateau. Like if I go to like hour 100 or day 100, looks like it's going to plateau at 2:30 if you keep scrolling down. So that's the answer actually to the maximum population, 2:30. So to grab the average rate of change, we want to grab the population at day 1 and the population at day 5. You probably just want to round to the nearest fly, maybe. So at day 1, we have what? About 6 flies. 1,6 flies. And at day 5, we have about 23 flies, right? So day 5, we have 23 flies. So we want to find the rate of change between 1,6 and 5,23 by doing y2 minus y1 over x2 minus x1. About how many flies did we increase by each day, right? 23 minus 6 divided by 4 days. So I went up, what is that, 17? 23 minus 6, 17. I went up 17 flies in 4 days. So my average rate of change is what? 4.25 flies per day, right? That's the average rate of change for question 1. Does it make sense how to get average rate of change? Because we did it a couple different problems, but I just wanted to make sure you knew how to do it. And then what is the instantaneous rate of change at 2 days? Well, if I'm in the table, how can I find an average rate of change if I only have one number? So they want to know how many flies were added to the population on day 2, basically. So what you do is you've got to change your table setup again. Go to table setup. You want to start at day 2. That's the day in question. But you want to make your delta table even smaller. You want it to be 0.01 for your delta table. So this is under second table setup above window. Start at day 2 and count by 0.01. Go back to your table. Now you're going to grab the 2 points on either side of day 2 as your y2, y1, x2, x1. So the 2 points we're going to use are 1.99. This time you want to use the decimals. 8.1976, 2.01, 8.2563. Do people see those coordinates in the table? I can't show both of them, but there you go. So those are your points that you're going to do y2 minus y1, and then you're dividing by 0.02 on the bottom, but you can do x minus x1. So tell me what the instantaneous rate of change is at day 2. So I'm going to do 8.2563 minus 8.1976 and divide at the end after I hit enter by 0.02. So tell me what one of you gets. Hopefully you do it. I think the only way to kind of get average rate of change and instantaneous in your head is if you do one of these calculations. Did anyone do it? To get 2 point something? Yeah, 2.935. So there's my y2 minus y1. I hit enter, and then I divided by 0.02 because I knew my x minus my x was 0.02. So 2.935 is the instantaneous rate of change. So that's how quickly the population is growing at that instant. And it asks, what day is the instantaneous rate of change the highest? We haven't looked at the graph. I'm just going to change my window from day 0 to day maybe 20, and my max to go up to, what do we say, 230, so 250. So I just want to show you what this graph looks like. Here's the population growth. It starts to grow very quickly in here, and then it starts to plateau off. So where do you think instantaneous rate of change is the highest? Probably in one of these several days right in here, right? So I don't know what that is. 1, 2, 3, 4, 5, 6, 7, 8, maybe day 9, day 10, or day 11, somewhere in there. So how can I justify that it's day 9, 10, or 11? Wait, I'm going to zoom in really quick. Let's go back to day 15. Maybe I can see it better. Oh no, it's kind of steeper in here, isn't it? 4, 5, 6, 7, 8, 9, 10, maybe 10, 11, or 12 is kind of the steepest area. So if you did day 10, day 11, and day 12 and compared them, I don't really want to spend the time right now to do this because I had a lot more that I wanted to review, but you would do like, go to day 10, for example. So let's see, 96.165 versus 95.751. That's day 10. If I go to day 11, let's see. This is 11727 versus 11684. I'm just doing the y values because I know if I subtract them, I'm just going to divide by 0.02. So what did I say? Day 12. Day 12 is 138.22 versus 137.81. So basically, which of those days has the biggest difference right around it? 96.165, 95.751, 117.27, 116.84, 138.22, 137.81. So it looks like it is going to be this middle day because the instantaneous rate of change, right, will be the highest when the y value subtracted is the highest. So see how close they are? I didn't divide these by 0.02, so 0.414 divided by 0.02. So instantaneous rate of change of 20 flies, instantaneous rate of change of 21.5 flies, instantaneous rate of change of 20.5 flies. So at day 11, it's 21.5 as the instantaneous rate of change. So day 11 is where the highest instantaneous rate of change is. And this is just a question we're going to keep coming back to throughout pre-calculus because it leads you into calculus. Calculus is finding the slope of the line anywhere on the curve to see where the change is happening at the greatest rate. So this is a precursor to calculus. So that took a lot longer than I thought. I'm just going to do one more of these on the video. So this is number 4. So I wanted to review what this stuff means and then have you do 5, 6, 7, and then you could try the quadratic graphs, I think, yourself to kind of end. So let's see. What is the name of this function? So you name it, remember, by its degree and by how many terms it has. So this one would be called a quadratic trinomial. Now, on some of these bigger ones, like you would just call this a 10th degree trinomial. Or down here, when there's so many terms, this one's just going to be a 6th degree polynomial. So there, there might not be a specific name for it, like this one has that specific name. The maximum number of zeros is always equal to the degree of the function. So a quadratic could have at most 2 zeros. A 0 is an x-intercept. It might not have 2. It might have 0 x-intercepts, right? But at most, it could touch the x-axis twice. The maximum number of turning points for a quadratic is 1. And that is 1 less than the degree. So your maximum zeros are equal to the degree. Your maximum turning points are 1 less than your degree. And then the right and left end behavior. So in standard form, your leading coefficient tells you what the right side is going to do. So if my leading coefficient is a positive number, the right side is going to go up. Now, the degree is going to tell you what the left side is going to do. So my degree is even. So what is the left side going to do? Also go up. So the right side is whether the leading coefficient is positive or negative. The left side, does the degree go even or odd? Right? So positive went up, even, they had to go the same direction. So that's a rule that you need to know about end behavior. And then a sketch of this graph. You could just use your graphing calculator on this page. This would be like a graphing calculator type question if you had to graph these polynomials. So let's see, this is 2x squared. Does that say plus or minus 3x? Minus 3x, minus 3x plus 4. I'm just going to go zoom 6. This is just going to be a quadratic, but so if I was going to sketch it, it's just a quadratic up here. So it actually didn't have any x-intercepts, but I said maximum x-intercepts it could have was 2. Does that kind of make sense how you're going to do 5, 6, and 7 the same way? And then I'd like you to finish in class 8 through 11, and I'll make an answer key to this page for you to check in a couple minutes. And then that's it. If you are caught up and you've already done 15, 16, and 17, you don't have homework tonight. I would say it's called a 10th degree trinomial because there's only 3 terms. 10th degree trinomial. If there's more than 3, you can call it a polynomial. For those of you completing this at home, I'm going to show the answers. So if you're not ready to show the answers yet, pause your video. Here's the answer for number 5. So you can pause it if you need more time. Number 6 and 7. Pause it if you need more time. 8 and 9. Pause it. And 10 and 11. And the only homework is to make sure you've completed 15, 16, and 17 from last week, remote learning. We're going to move the test a day. So review will be Tuesday, team test Wednesday, test on Thursday.